Hey y'all, welcome to Miss Clark's chemistry class. In this series, we're covering everything that you need to know about gases. I've already released a lesson over kinetic molecular theory and Boyle's law. This lesson here, all about Charles's law. Charles's law deals with volume and temperature. You're going to need your notes, you're going to need a calculator, and something to write with. Let's get started. We're still talking about these gas laws. And remember, the gas laws are going to be based on observations that describe what? What do we see? What are gases doing? How do they behave? But remember, the kinetic molecular theory is what describes why gases behave the way they do. And once we understand why the gases behave the way they do, it's a little bit easier to understand what we're observing. So make sure you've checked out kinetic molecular theory. Okay, so let's talk specifically about Charles's law. And Charles's law is going to relate the two variables volume and temperature. Okay, so if we have this container of gas and we put a Bunsen burner underneath it, these particles, they're moving with a certain amount of kinetic energy. Okay, so remember, we've talked about with the kinetic molecular theory that when we increase the temperature, that increases the kinetic energy. And if these gas particles' kinetic energy is increased, so if we're increasing this fire and making it hotter and hotter, then these gas particles are moving faster and faster. We can show that with larger arrows. If they're moving faster and faster, if we're only talking about volume and temperature, we do not want the pressure to change. We want the pressure to remain constant. At this point, the only way that we could make the pressure stay constant is if we make a bigger box. We need our container to get bigger. So as we increase the temperature, those particles are going to start moving faster. They're going to start having more and more collisions. So that means our container has got to get larger so we can minimize those collisions and keep the pressure the same. So for Charles's law, since we are only talking about temperature and volume, as the temperature increases, the volume also has to increase just so we can keep the pressure constant, and vice versa. If we lowered the temperature, these gas particles are going to start moving slower, having smaller, less collisions, and so the container would be able to get smaller and smaller and smaller. I'm going to show you an example of this happening. Okay, so I have two examples of Charles's law. Charles's law compares volume and temperature, also directly proportionate. Y'all, a secret is if it's got temperature in it, it's directly proportionate. Okay, so volume, if volume increases, temperature increases. If temperature decreases, volume decreases. And that's what I'm going to show you. Blue liquid in the bottom of my plate. Just blue so you can see. Okay, now we've got to create a temperature difference, so that's why I'm going to light these candles. Okay, so I'm going to create a chamber using this flask, and when the candle is going in the flask, it is going to increase the pressure inside of the flask, which is going to hold the water down. As soon as the flame starts to go out, that temperature is going to decrease. And when the temperature in the chamber decreases, so is the pressure. And then let's watch to see what happens when the pressure decreases. So you can see we created a vacuum chamber. Pretty cool, huh? Let me show you another example of Charles's law. Let me light my Bunsen burner here. Okay, so I've got a soda can and I've got a little bit of water inside. We're increasing the temperature of the can. Then I'm going to plunge it into ice water, and we're going to see the effect of an immediate temperature decrease. Think about what's going to happen as the temperature is decreasing. So when we very quickly reduced the temperature, we also very quickly reduced the pressure, crushed the can. Pretty cool, huh? Should we do it one more time? Okay, well, I hope that helps you to understand Charles's law. Let's look at a math problem and see how that works out. A balloon takes up 625 liters at 0 degrees Celsius. If it's heated to 80 degrees Celsius, what will its new volume be? Okay, so a couple of things as we go and identify these variables. So I reread my problem and I find my first number, 625 liters. Liters, that's a volume. So my first volume is 625 liters. Now here, this temperature, that's temperature 1, except for it's in Celsius. That's a problem. Remember, we need to add 273 to that because we need Kelvin. 0 plus 273, that's just 273. Kelvins. Let's keep reading. It's heated to 80 degrees Celsius, so that's our temperature 2. But again, that's 80 degrees Celsius. We need Kelvin. We're going to add 273 to that, and I'm getting 353. Okay, so now we're ready to use our formula. Volume 1 over temperature 1 equals volume 2 over temperature 2. Again, I just put these straight into the problem. So volume 1, that's 625. Temperature 1, that's 273. Now, I have T2, so I must be looking for V2. So T2, that's 353. Now, this looks exactly like a proportion. And if you need to think about this V2 as an X, then just put an X there. So we are going to cross multiply and divide. Proportions, cross multiply and divide. Do we remember that? So 625 times 353 divided by 273 equals my X, or better yet, my volume 2 is going to be 808 liters. And let's look. Our temperature, that increased. This is directly proportionate, so we would expect an increase in our volume, and it did. This looks good, and it's also in 3 sig figs. Let's look at one more example. On hot days, you may have noticed that potato chip bags seem to inflate, even though they have not been opened. If I have a 250 milliliter bag at a temperature of 19 degrees Celsius, and I leave it in my car, which has a temperature of 60 degrees Celsius, what will the new volume of the bag be? Let's go through and label all of our numbers. The first number we see, 250 milliliters. Milliliters, that's still a volume. 250 milliliters. At a temperature, so here is my first temperature, T1. 19 degrees Celsius. That's right. We cannot leave that in Celsius. We've got to add 273 to get kelvins. 19 plus 273 is 292. I keep reading. The next number is a temperature. That must be T2. 60 degrees Celsius. Again, 273. And I'm getting 333 Kelvin. Okay, so we're dealing with volume and temperature. They're directly proportionate. So we would show that as a proportion. Volume 1 over temperature 1 equals volume 2 over temperature 2. So V1, that was 250. T1, that was 292. V2, that's what we're looking for. I'll put my X there. T2, 333. So again, we're going to cross multiply and divide. 250 times 333 divided by 292. I'm needing 3 sig figs and I'm getting 285 milliliters. We showed that our temperature increased, so our volume increased. This looks like a good answer. Okay, so that was Charles's law. Again, make sure you understand the concept behind the relationship between volume and temperature. Also, make sure you can work those calculations using Charles's law. Stay tuned for the next law, Gay-Lussac. Until next time, bye y'all.